Hello, can you hear me? Okay, let's see if this actually works. It looks like I'm sending audio. Hello. Refresh. This actually works. Ooh. It looks like I'm sending. Let's see if I can like wacky ass sound. I don't know where the interference is coming from, guys. Hello. Filters. Refresh. This actually works. Ooh. It looks like I'm sending. Let's see if I can like wacky ass sound. Okay. Well, that may or may not be working. I gotta turn this off so you guys can't hear the stream. Yeah, so right now I've been trying to get some work done. I kind of want to create a little storage thing. So this is kind of a little storage thing. I think I'm going to dump a lot of vapes in it. It's based off, I'll show you guys. So, don't mind the trash in here. But this is just a model I found online, and it looks, I thought, very cool. It's very simple. It's almost too simple, actually, because it has so many downloads, that I'm basically going to make almost the exact same thing. And then, check this out. I'm adding a lid. So right now I'm working on the lid. And I've also added this chamfer to the bottom because I think it looks cool. Yeah, mine's not exactly the same, but it's pretty much exactly the same. I tried making a big box like this before for this for my senior project I'm doing, and thing is, these actually, and I've also these ridges actually do something. Believe it or not, to the bottom because I think it looks cool. So, just realized my audio isn't that good. You guys will probably hear that. I don't know what that freaking. I don't know what that mic sound is. We'll see if that fixes it. Maybe I can add a filter here. Okay, so there's now a filter on here, and it looks to be pretty good. Mine's not. We'll have to give that a try. Okay, but anyway, this is the box so far. Right now I have now that will turn that off. Right now I have this. Looks okay. And what I was working on was this sketch right here. So I basically want, I think I want to do this. We're going to do a center point rectangle. Here we go, right on the center line. We'll go, it's 12.5 millimeters. This thing's 180 millimeters wide, 60, 120. What does 120 look like? Oop. Let's try 90. There we go. Looks good. So here we will take this. Copy it. Create another sketch. Not paste it, but pretty much do the same thing here. This is honestly, there are people out there who are like crazy good at this shit. Actually, most people who actually do this are probably better than me. And I'll admit that happily. But knowing like just I think even a little bit of this like skill is extremely useful. I mean, being able to like design something and then like fix a part is just one thing, but like I don't know. It seems like they should be teaching like 3D design like this in school. I mean, they do, to be fair. I got taught like in middle school, but I'm not too good, I'll be honest. So we'll see what kind of looks good here. I just kind of do what looks good too. Like I don't think I could actually do this as like a machinist. Like I'm not good at well, I mean right now I'm not good at machining, but machining is like such a daunting task. It's insane. Like I don't know. Every machinist out there, you guys are on a whole new level. I can't believe it. I work with a guy who used to be a machinist and is actually kind of crazy, believe it or not. Like such a daunting task. It's insane. Yeah, that filter sounds a lot better. Um, but yeah, this is what I've been working on. We're gonna go for a fillet here. I've heard people like obviously it's spelt like fillet, so I don't actually know if there we go 6.25. That looks pretty good. I don't actually know if it's fillet or fillet. Like I know you fillet a fish, but do you fillet a 3D do you fillet a 3D model? I don't think so. If there are anyone that knows, feel free to like let me know because that's pretty cool. Or it might be a pretty cool thing to find out. Oh my god. I need to get one of those like gyro balls. Okay. God damn. I can't remember. Did I do a 5 millimeter fillet? 6.25, right? I did say that out loud. And there we go. So yeah, this is looking pretty good. I guess I could have done the fillet on the sketch. That would have been a bit faster. Um, Whatever. You know, you reap what you sow. So you reap what you sow for something so like benign. Thank you. God, I'm gonna get like some sort of arthritis in my finger for scrolling so much. Can feel it beginning already. At least I won't be surprised when it happens. Oh my god. But yeah, I don't know. Streaming, it's kind of honestly, like I've kind of said before, it's more like just journaling. I mean, I don't really have a whole lot like interesting maybe to say, but it's kind of nice just like having it all said somewhere. And I think for me, it's like okay, yeah, whatever. I don't really get too many views, and my thumbnail is not that crazy. But like the amount, I don't know, the amount of work that goes into like YouTube video making, like what? Okay, um, yeah. The thing about that is like it's so hard now. I think to like do things on YouTube. Well, not like too hard, but like it's so competitive now. Like everything is so competitive because everyone just uploads everything to the internet all the time. I mean, it was competitive back in like it's always kind of been competitive, but it's just like you're either insanely lucky or you're insanely good at something and there's really no other like reason people will watch. I mean, unless you have like something very you either have to have something very niche, need to be very entertaining, and then you can do whatever. Or and by usually entertaining, usually pretty funny, or you need to be really good at something, or any combination thereof. And That's like essentially what it means to be a like uh like someone popular on the internet. I think those are the criterion. So I have this lid now, and I think this will work well because the plastic is pretty flexible. So we have two bodies. Yes, this is the actual lid, and this is the this is the lid because I thought I was gonna make the lid first, but it made more sense to do this first. So this thing barely fits on a single one of my print plates. So what we're actually gonna do is we are going to, let's see here. We're going to take this body. We're going to save it as mesh. Okay. We're going to call it lid. Save. And then we're going to do the same thing with this body here. Save as mesh. There might be a better way of doing this. This is the fastest way I found to like export these things. Box. I usually save things as box lid. Just one word. And to be honest, I'm mostly making boxes and the lids. So that kind of ends up being a very poor strategy. I'm not going to lie. But depending how this turns out, if I can size this, basically this is the full build volume of my bed right now. So I could print this full size. I'm going to do a half size print. And we're going to see how that turns out. Oh, and by the way, in 4 minutes here, I'm going to have to head out quick because I gotta blast. You know, like what if you just start like a live stream and like you just leave the camera on? Like while you're at work or something, and you leave the camera on and like every day it's like, I mean it literally would be like the Truman Show. You're just constantly streaming. It never ends. That might be something. Hmm. Like when you go to work, you like actually go to work. I know people have done long streams before, but I think it's just kind of funny. It's like literally a Truman Show. Uh, like just someone's life. I think if you start doing that, you might actually. That's actually probably a pretty good idea. I think that shit would just like blow up on the internet. Just like the never-ending live stream. Every encounter you have, it's like, do you really want all that to be on the internet? Everything you do, say, and think. I mean, you'd be literally knowingly putting yourself through living through kind of like a simulation, like literally Truman Show level shit. Okay, now that we have them saved, though, I want to fit both of these on the build plate. So if I size them at 45%, they should be able to fit just fine. So we're going to file, import, 3D step file, box lid, open. Yes. We're going to split to objects. We're going to size everything to 45% because this thing would take way too big or way too long to build otherwise. Not that much. Sort. The thing is, it's pretty cute. Ah, empty initial layer. Oh man, it better print something that's like 0.5 millimeter. There we go. We'll see if this little thing works. Let's go with extra draft. How long is that gonna take? Oh, an hour. Okay, that sounds about right. Holy crap. An hour. An hour to print? Really? I bought this fast stop printer just for that. A whole hour, please. A whole hour. Okay. Will I go? You guys can watch this live. It's actually been going. Can you believe that? Holy crap. Hmm. Interesting. We'll see. See how that turns out. But yeah, I've also been meaning to create a. So this is my senior design project. That's what I've been working on. I have this little board here, which is pretty cool. I've also it's a current sensor. So it actually measures current. And I also have a battery in here. So the goal will be to test batteries. This one, what I want to do is I want to have alligator clips Um, yeah, it's just I need the power resistor is what I need. So I also need, yeah, I need the power resistor because of how many ohms it is. And that doesn't come until late October. So who knows? But right now, this battery and this giant freaking this thing's crazy. Hold on a sec. This giant freaking like wad of resistors I made. So technically this actually works because well actually it might not, but it just barely works. And I'll explain why. I have to take a picture of it though. And let's go down here. Did I put those on here? Okay. I'll have to do this again. This is so crazy. Uh, okay. So the reason I put this into the can I hold on, let me do this quick. This will be kind of cool. Is this really how low quality this is? Well, anyway, the goal here is to. Oh, why is it so bad quality? Yeah, I know you can see my freaking crotch here. So, I'm taking pictures right now. Oh, what is that? What? Isn't that crazy? How did I get there? Yeah, this watch is actually pretty crazy. I got it for really cheap, so we'll see what happens. Um, yeah, pretty much. I have to get this to. Can I just like change the? What the heck? What? Okay. What? What's that? We'll send it backwards. Send. We'll get this out of the way. Yeah, I'm sure. Did it look like I'm not sure? Yeah, this is bad news. It's just arbitrarily placed. There we go. That's what I wanted to do. Okay. So, I have to upload our pictures here to the also yes, we need to take more pictures. And give me 1 second. I need to do Duolingo here. Yeah, it's bad. I'm not very good, so bear with me.
Praten. Woonkamer.
Slaapkamer.
In probleem. To eat. Ik hoop dat je eet. I hope that you eat.
Werknemer.
Baan. Burgemeester.
Volgen.
Begrijpt. Begrijpt. That's understood. Tell. Oh, tell.
Er schrijft iemand met een potlood.
21.
90.
Studeren.
Slaap. Soms vergeet ik mijn naam. Soms vergeet ik mijn naam. Ik.
Mijn. Naam.
Jij.
Potlood. Volgen. Gebeuren.
This is really bad.
Het schaap volgt de boer. We vergeten wat er belangrijk is.
Vergeten.
Wat?
Er. Belangrijk is.
Er zit
Is it in 3600 seconden in an hour? In an uur. Oops. The spiegel. Done. I'm done. Okay. So what we need to do is we have the circuit board here, and we need to plug it in. Actually, we won't plug it in just yet. One sec. Okay. Where was I? So, yes. The idea here is this is a 10. So, okay. So basically, I'm testing the power of the battery at roughly 1/2 C. And since this is about an 800 milliamp hour battery, it can sustain a load of half of its capacity in milliamps for, an indefinite amount of time. It doesn't get hot, essentially. If you're running it, drawing more current, you're going to be pushing more amperage. You're going to be creating more heat. And in that process, you can damage the battery. You can damage your system. I'm running it very conservatively. Another reason is having it be at that level is I need this sensor to be able to sense how much current is flowing. The idea here is that it will take too long, or it will take about 2 hours to drain the battery, but this doesn't measure above 400 milliamps, which is the biggest problem here. That little freaking i2, was it the INA219 sensor? And yeah, I do have a problem with that. I actually do. It's quite annoying. It's quite annoying. So how do you solve the problem that this can't actually measure 400 milliamps? Well, there's a few things you could do. You could get a different sensor. Hey, I got a sensor now that is, I can't believe how bad this looks. It's probably better just to stream my phone as an input. But yeah, we'll put this down here. So what do you do if this sensor doesn't actually quite fit? Well, or if this sensor doesn't measure enough current? Well, you can either increase your resistance so you have less current to flow, or you can get a different sensor. Which one do you think I picked? Not the different sensor, actually. That'd probably be the smarter choice. No, I got an actual power resistor of 12 ohms, and we can do the calculations here. This is actually a very easy calculation. As an electrical engineering student, this is one of the simpler ones. So basically, the idea is you have a voltage of either 4.2 volts or 4.2 volts at the peak, or 3 volts at the minimum. So right now, if you want a constant current, or if, let's say, we're not going for constant current yet. With this design, this doesn't drain current constantly. So what do? We can, let me think here. So with the 4.2 volts, right? 4.2 volts at the peak battery, when the battery is fully charged, it will discharge at half C, which is, right, 400 milliamps. And how do we get to 400 milliamps? Well, since the peak voltage is at 4.2 volts, you can really easily get to 400 milliamps, you know, sustained current by just building or plugging into a 10 ohm resistor. So this resistor here, I have custom made to be 100 or 10 100 ohm resistors in parallel, which basically means there's calculations you do it. It's basically the inverse plus the inverse of all of the resistances, and then add those together and then inverse it again, and that's your total resistance. If you do that with all the same type of resistor, or all the same ohm of resistors, you'll just basically divide by how many resistors you have. So if you have two 100 ohm resistors, you take how many ohms you have, which is 100, divided by how many paths it can take, which is 2, and you get 50 milliamps per path. I have 10 100 ohm resistors, so you take 100 ohms divided by 10 the amount. That only works if they're all the same resistance. If they're different resistances, then you add the inverses and then take the inverse of that. Now, with that being said, let's show the calculation. 4.2 volts, right? Divided by 10 ohms, you get 0.42 amps, which is 420 milliamps. So this amount of current is too much, right? For the 400 milliamp limit on the what is it? On this little sensing board right here. Great. That's great. So it's exceeded. So what we can do is I ordered basically another reason this has to be 10 resistors. Oh, you could have just used one small 10 ohm resistor, couldn't you, Zach? Well, let's look at it this way. If I were to, let's say, if I had a 10 watt resistor, now remember, these small ones are only rated for 1/4 watt. If you go much higher than that, they'll just burn up, right? So each one is rated for only 1/4 watt. Probably it could go a bit more, especially if you're cooling it, but just open air, it's rated for 1/4 watt, which is not a lot. It's actually a very small amount of power. It's like 1/700th of a horsepower is 1 watt. So this is rated for 1/4 of 1 watt. We can actually ask Copilot really quickly. How many, continue, just take my data, please. How many horsepower per watt? 745.7 watts. So it's roughly 1/3000th of a horsepower is how much energy, how much power this one resistor can dissipate. Now I have 10 of those resistors in parallel, which means in an ideal world, it would be able to dissipate 1/4 watt times 10, which would be 2.5 watts. Now, that is more than I need right now, but 2.5 watts is if they're all open air. They're all wrapped around each other, meaning that heat can't escape as quick. So, what's up happening is you need to dissipate all of that heat you need to dissipate all of that heat with less surface area, right? So because they're all crammed together, that heat needs to go somewhere, and it can't escape really easily through the resistors because there's a few that are completely surrounded or not all sides are facing, open air. So yeah, it's going to get pretty hot. So I would estimate that this is definitely probably at around a 2 watt maximum resistor. I don't want to push much more power through it than that because it will burn. And I don't want a fire right now. Believe it or not, I don't really want a fire tomorrow either. Okay. And let's see here. Okay. So yeah, we have 2.5 watts. So let's say we're running that at 4.2 volts at its peak, right? That's 420 milliamps, right? And an easy formula for your current or for your actual power is your voltage times your current. You can also do your current squared times your resistance or your voltage squared over the resistance. And those are just gained by getting your they're just gained by moving around the Ohm's law equation, which is voltage equals your current times your resistance. Now that's almost always ideal in a perfect world of perfect conductance. So yeah, let's see here. Okay, whoops, wrong page. If you want to check that page out though, guys, great page, by the way. 172 downloads, guys. 172. Great stuff out there. So yeah, we have I squared. We have an amperage of 0.42 amps times our voltage of 4.2. And we need to dissipate 1.76 watts in a very small place. No good. No good at all. So, yeah. So that's what this is made to do. And believe you me, this thing gets hot. So I did a couple tests with this before, and it's pretty simple. We'll hook up the current here, or we'll hook up the, let's get this on the big screen. Yeah, I know it's really pixelated, okay? Don't mind. Please don't mind too much. I don't know why it looks so bad, but whatever. So we have this. And basically what we need to do is we need to have the current out of this battery, right? Run through this sensor, run back. So it needs to cross over to the sensor, cross back, and needs to go through this resistor. And then it needs to go back to the negative terminal of the battery. So what we'll do is we'll probably do it like this. We can put those together. Let's not. It doesn't really matter right now. So we have our positive end of this running through, right, through here. One side of this so far, but we haven't connected the other side to ground yet. And I will show you why that is soon. First, we'll get this back going, this stream. Give her this calculator. We'll open up. Oh, you guys want to see how this is going? It's going pretty good. I have to open up a Tawny project, test improved. So this is the program I have asked ChatGPT to make by feeding it a bunch of libraries and having it output me something very useful. So what this does is it communicates with this little board, this little Raspberry Pi. So this is a microcontroller, which means that I can code it and all of these little pins on it, I can make them do whatever. A more skilled person can make them do more stuff. I'm not that skilled, but you got to start somewhere, right? So what we're doing here is this is the code. It is AI generated, but it's fed off of code that was written, kind of libraries that have already been written, and basically what I want to do. And I've edited it to give me some more information. So this here, this shunt value, this is not very useful. So, but I'll print it off anyway. So the bus voltage is useful, current, this is all useful. So we're just gonna run it. So basically what it says is, this is what the sensor is sensing right now. So relative to ground, the battery is at 4.32 volts, which is I think that's slightly above 50%. So it's probably like almost fully charged right now. It's almost fully charged. But when we start drawing current through this battery, you'll see the voltage drop. And that's just because when batteries actually drive a load, there's current leaving. The battery isn't a perfect current supply or a voltage supply. It has its own internal resistance. So instead of having just, two ends of the battery not connected to anything, now you're drawing current between the internal resistance of the battery and whatever load you're driving. So the current inside ends up dropping. Basically because now you have a very small resistance in series with a large load. So basically what you're measuring is between two resistors. You can't measure you couldn't measure the internal resistance of the battery, but it's easier to measure you can measure it. I don't know what I'm trying to say. It doesn't really matter. Point is, let's see if this is still going. Yeah, okay. Point is that this thing, let's just get to this. This thing measures current. So when I plug this in, since we're at 4.32 volts right now, this will drop soon. It'll drop when I plug it in, which is a little annoying. So this will drop when I plug it in, this voltage. The shunt resistance, this might be better measured. This is basically what it's measuring across like the shunt resistor, and then it's multiplying it to get this, or the shunt voltage, and then it's like calculating basically right here. So let's see here. The current, 0, of course, because it's not, and the power 0 as well. So, because it's not running right now. So we're going to run it through this 10 ohm resistor, right? At 4.032 volts, and we're going to measure the power. We're going to double check and make sure that this is running correctly. So we're just going to do some cross-checking. I'm going to plug this in. And here we go. Okay. So as you can see, the current dropped a little bit here. Let's see here. I'm going to screenshot. I'm going to screenshot this transition right here. Actually, rectangle. There we go. Transition where the current is put in. Okay. That will go in the OneNote for later. Okay. So basically, this is the power being read by this resistor. This thing is hot, very hot to the touch. I mean, it's not like too hot right now. It's very hot to the touch. Basically, it's kind of crazy. That's a lot of wattage for this small of a space. But what we want to check are some, critical things. Is the battery getting hot? It shouldn't be, because the current is driving at a very conservative rate. Want to check, is this what we expect to see? Is this what a value we expect to see? So let's look at the calculator again, which I know I closed. Is this a value we expect to see? So we're measuring 394 milliamps, which based on our 10 ohm load does look about right, because it's 1/10 roughly very close to 1/10 of the voltage that's being measured. So just by inspection, and this is, we also know that this voltage is in a nominal range, right? Since the battery was charged when I had tested this before. So I had tested it down to nearly 4 volts because I ran it for a little bit before. So we know that this is an acceptable voltage range. So based on that, our current looks great. It's about, just by inspection, it's about 1/10 of the voltage we're measuring, which you would divide your current by your resistance to get your voltage, or sorry, your voltage times your voltage over your resistance to get your current. We have power of 1.5 watts. So if we do a quick calculation, we can do, remember, we can do voltage times current to get power, which should give us this value. So we have 3.1, sorry, 912, 3.912 times, what do we want to times this by? Times our 0.395. So we have a power that is looks very good. It looks very much like what we're seeing here. So we can confirm that all of our outputs are correct given a 10 ohm load. And yeah, this shunt resistor is basically what voltage is across a very small resistor. So it takes a little bit of power, obviously, to read this stuff. So what it's measuring is this very small voltage here. And basically, because the chip has a known size shunt resistor, it can do all the math on board, or actually, I think this program is doing the math right here. So yeah, pretty great little bit of code here. But yeah, this little resistor is spinning 1.5 watts of heat right now, which, when we discussed if you want to put that amount of power into perspective, a 1 horsepower motor is about the size of a sizable electric bike. So that's how much power a sizable electric bike can put out. This is 750 divided by 1.535, about 1/500th of a horsepower. So yeah, it's about right. It's just a little crazy. We're getting some good progress, guys, on the print right now. This is looking great. Actually, I hope this works because it looks very fun. And yeah, I just think it'll be cool to have like a little box like this. So if this turns out good, I can just like scale this. Generic PLA. Okay. I can just scale this and put it on my printables. So yeah. I'm not really like huge into this printables thing, but I did kind of make some things that are pretty cool. This one didn't quite turn out right. I mean, it does look like it turned out right, but it didn't actually like fully print out. So then there's this one. This shelf literally took me like, I mean, not to boast, guys, but this thing took me like 5 minutes to design. It's literally just like, I literally drew about the thickness of the base I want to be, which this is kind of thick, but it's only 5 millimeters. It's whatever. And then I basically drew another line up here, another 5 millimeters. This is 10 millimeters, a centimeter in height from here to here. And then I drew a spline. I drew this up like just some arbitrary number and then drew a spline like this. And yeah, it prints upside down like this. But crazy thing is I actually intended the design to be like this pictured here, where it has this little lip. So if you put stuff in here, it won't fall out, like small things. Turns out you can also put it like this, and it works just the same. You just don't have that lip to protect things from falling off, which is kind of like, whatever. But yeah. So what else has been going on? So yeah, that's what this box ended up being. And it's looking pretty good right now. Although we'll have to see. Let me check quick. This is like literally like just a baby version of what I had in mind. We'll see if it turns out good though. I think it should. I don't see why not really. But yeah, so we'll see how that turns out. So now as this is dissipating heat, you can see the voltage has slowly been going down. We can measure around to 5 millivolts, which is pretty impressive actually. Now that I think about it, that's pretty good. So we'll see how to print in a. So this is what's going to be cool. How .csv format. Okay. Okay. Okay, this is actually not too bad at all. Interesting. Okay. This will be really cool. So what we're going to do is we're going to go back to Tawny. We're going to collect all of this. We're going to hit File, New. We're going to file. Okay, so now we have a. This is the test improved. So what we want to change in here, there's just a few values. So basically what we want to do is we want to have. Let me get this back up and running. So while this discharges, we want to collect data on it, right? We're going to file. Okay, so now we have a. So basically we want to collect data on how this board here is discharging or how this battery is discharging. So we have a known load. I mean, none of this actually matters once we can start collecting the data. So now we're collecting data. We want to take the data. We want to, well, okay, sorry. Now that we have these values we can read, we want to collect data. So this is the format for a comma separated list, a .csv format. So you have this right here. This is the list, or comma separated list is a common separated value. It's a plain text file that stores tabular data where each line represents a row of data. So we can just make a text file, right? We can, instead of having to go through all the steps of making a test file and yada, 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 and have it print out nicely, we can just print it like this. It's pretty simple. So okay. Here we go. Okay. So I'm going to put this off to the side. This is what I'm using for reference, so you guys know. We are at about 1.5 watts now, and we're going to stop. Well, actually, we'll just let it keep running because this has to drain anyway, so I can charge it back up and test it again. Yay! We can do here. Let's see here. What do we need to change? So prints this. We'll stop this quick, and then we'll see what it prints again. I'm not really sure. Yes, because this is AI generated. I2C error number 0, timeout. So that happens after this is printed. Which is really kind of annoying, but whatever. It doesn't really matter. Start this again. Okay. Maybe I'll have to go back and change that quick, but it looks like maybe. Hmm. Okay. So yeah, what it's doing is it's printing this here. Let's just get rid of this. Really, bruh? Okay, so it errors out the first time. Can I just make it like wait? Let's just make it wait a second beforehand. Like, oh my God. Why does it do that? I don't understand. Maybe make it wait longer. Okay, we're just gonna undo this. I think it has to run. It has to be able to try this first, and it can't try it like right away. I don't know. It's not a big deal. What we'll do is we'll add a variable here, and we'll call it check equals 0. We'll put this in a big if statement. We'll tab this over. We'll type here if actually we can just use this to our advantage. What am I doing? Okay, okay. We're going to print this as, let's see here. We want to print this as there we go. Okay. Stop. Run. We don't want to be changing this one. We want to be changing this one. So I2C error. We're going to print that. We're going to print first voltage, comma, current, power. And now we'll stop current power. And then this fourth column here, we don't really care about that fourth column. So what we're gonna do is we're gonna have it print off, and if there's an error, it will print that. And then below that, we're just gonna start printing all of this. We're going to get rid of the shunt voltage. The shunt voltage. So here will be a 3, this will be a 3, this will be a 3. This will be gone. We just want our current, our voltage, our current, and we want to change all of this to just a %3, the comma in between, and bus voltage. So that should be good. We'll get rid of the watts. So now it's perfect. It's literally perfect. That's it. Now we'll file, save as this computer. We'll do downloads, desktop, senior design, INA 219 CSV .py. Save that. So now this is our CSV file, which prints directly to a CSV. And maybe we want to change this time here. So this time basically is how this time here is. We can change this at the top. We'll add a, I'll call this data. Let's see. Let's actually ask ChatGPT. What would be a good name for a variable in Python that when changed changes the amount of time between data logs? Log interval. Well, when you put it like that, ChatGPT. So we're going to say this equals we're going to set this equal to 5 seconds. There we go. And then we're going to say this is equal to log underscore interval. There we go. Stop and run it. Should get that 1 after 1 second right away. And then every 5 seconds after. Looks like it's working pretty well. So yeah, we're just going to let this run for a bit and we want one more thing. Log interval. So we're going to need a time variable. Okay, that'll be good. print, it'll time sleep internal. And then after this, we're just going to copy this. Well, how do we change this? There we go. And we're going to do here, right before reset, time score total equals time score total plus where was it? Log interval. There we go. It's a pretty simplistic way. %f. Let's try that. Can I do that in I as an interval? Is that what that is? There we go. I'll let that run for a while. So I also eventually want to add a switch to this. So when you plug it in, it will basically, this will go if the voltage is above 0. So as soon as you plug it in, boom, it goes. Now you get a consistent test every time. Yeah, it's not very interesting data. I'll be honest. You probably log it every 10 seconds. That might honestly be better, because this is like way too fine. But now that we have this new and improved file, save as this computer, save, yes. So we'll just do a file. What? Anyway. So now we can just change our log interval to 10 seconds. Now it should go 0. This is what it's like, guys. Logging data points. Now we wait. Looks like the box is almost done. So yeah, now you can see our current has gone down quite a lot. But it's still within our range. So the thing that's annoying is like if this were 500 milliamps, I wouldn't run into this problem where I could just use the 10 ohm. That thing is hot, guys. It's very hot. Yeah. That's what's going on. Pretty cool. Pretty cool. I wouldn't run into this problem where I could just use the 10 ohm. Whoops. But yeah,
hot,
so
guys.
It's very hot. I don't know. We'll see how this data turns out. It'll be easy enough once it's in this form to just put it into a spreadsheet.
That's what's going on.
Pretty cool. Voltage, current, power.
Cool.
Crap.
I wouldn't run into this problem where I could just use the 10 ohm.
Whoops. But
Stopping
yeah,
is
so
hot, guys.
whoops. That's gonna be going for a while. My bad. Time. Voltage, current, power, time, and then this should be in a column of its own, and then it can just get removed. Except there shouldn't be a comma there. The heck? Okay, and go. Now we're collecting data. Oi, I gotta send this to my... Let's see here. Let's get this going. Let's get this going. This going. Can I get the big screen? Can I just show something quick? I don't know why it's like lines like that. It's weird. Okay. Storage. I can just access the storage like that. I guess I don't know why I couldn't. Anyway, right back. Oh. I guess it didn't even play. As you guys can see, it is pretty much printed, which is pretty cool. It's nice that it takes data like that because it's so simple to like just print that off. Like literally so simple. You can see the thing has quite a bit of power in it. You're not gonna lie. Like it really shows you how much power we're generating. Oops. We're back again. This time, let's watch both. As you guys can see, it is pretty much printed. Yeah, so with this data, like having it like this, you can very easily extrapolate the total power, which is kind of cool, actually. Kind of cool. Or the total amount of energy in the battery in joules. I don't really know how I haven't shown off 4 concepts of electrical engineering yet with this, but who knows anymore. You did just notice the print is done. It's done. So, no. Oh my god. It's been going on for 6 minutes now, almost, guys. 6 minutes we've been collecting data. So, yeah, what can I say? I think I'll probably end the stream here, though. This has been a good kind of session on getting a lot of this stuff done that I need to for my senior project. There's a lot of work to do. Still more to come, but this circuit essentially is like a very simple battery tester, which is great. And once I have the 15 ohm resistor, icing on the cake. It'll be great because then I can test at a constant current. All right. I'll see you around, guys. See you around.